theory acquires a very different kind of flavor. I mean, all the results I have here for crystal higher genus have sort of to do with proving that rational points cannot exist, that there are finitely many or few in some sense. So we kind of look for obstructions to the existence of rational points. But I think a point that was made, for example, in the lectures by Professor Newholz concerning the circle method, is that this kind of in the study of Diophantine equations, there are two kinds of theorems. There are results where you try to show that rational points do not exist, or that there are few rational points. And there are results, there are theorems where you try to show that rational points have to exist. So a typical example is what comes out of the circle method. Of course, the circle method is concerned with equations where there are many variables, where the number of variables is large relative to the degree. So it doesn't really apply to the case of curves, where essentially we have only one variable. But for curves, whether characteristics strictly positive or equal to 0, we're going to see that actually we can strive at least to obtain results of a similar nature, sort of existence results on actually constructing rational points. And that's going to be sort of the main goal, I guess, in this week, and to explain that in this week's lectures. So I'm going to begin then. Let E be an elliptic curve. So a curve of genus 1 equipped with a rational point over K. So elliptic curve over a number field K. Okay. So that's a curve of genus 1 with a rational point, which I call the origin. And then once I do that curve is endowed with a natural structure of an algebraic group, as we already saw or discussed many times last week. So we want to understand, of course, so the question is to study the group E of K, or more ambitiously, the set of groups E of L, maybe as L ranges over all the finite extensions of K. Even infinite if you want, of course. Okay, so that's what we want to do. Now, the most basic result in the subject, of course, is the well-known Mordell-Weil theorem, which asserts that this group is finitely generated. So, Mordell-Weil theorem. The group E of K is a finitely generated abelian group in part. So, i.e., we can write E of K as a direct sum, non-canonically, but as a direct sum of a certain number of copies of Z, R copies of Z, and a finite subgroup. This one is canonical. This is the torsion subgroup. Okay, so cardinality of T is finite. Okay. So, that's clearly the basic finiteness result in the subject. I'm going to say a few words shortly about the proof. But the point I want to make now first is that, okay, so we know a lot. We know a lot about T. Well, in fact, we already saw that last week, of course, in the lectures of Marussia Reboledo, who discussed Merel's theorem. We know that there exists a constant. So the cardinality of T is bounded by a constant which depends only, in fact, on the number field K. In fact, even more, only on the degree of K over Q. Okay? And in any case, for the game we're playing now, where you fix an elliptic curve and you try to study this torsion group, there are very good algorithms, very efficient procedures for calculating T given E and K. So somehow, from the point of view of the kind of questions I want to discuss this week, the group T holds little mystery. But, so the real mystery is in understanding R. So the sort of the mystery in the theory of elliptic curves is sort of to understand the variation in the rank. I'll mention shortly a few natural questions. For example, how does one compute effectively R, and so on and so forth. So this is really the sort of invariant, which is subtle, and which we'd like to get some kind of control over. Now, before doing that, maybe I'll I want to say a few words about the proof of the Mordell-Weil theorem. Okay, so some words about the proof. I'm not going to go into the details. So, I mean, the idea is, and in fact, I mean, this was already implicit in some of the exercises I assigned last Monday. I mean, the idea is to exploit the fact that the elliptic curve E is equipped with many unramified coverings to itself. Namely, by virtue of the fact that it's a group, the multiplication by n map is a nice étale cover from E to itself over spec K, but in fact, this even extends to a smooth morphism over the spectrum of the ring of integers where we invert the primes of bad reduction, the primes dividing delta, and the primes dividing n. Okay. So last week we kind of saw that if you had an unramified covering of curves, y to x, we could exploit essentially the fact that any rational point would have, the fiber of any rational point would have a bounded ramification to prove results like if the curve upstairs is Mordelic, then the curve downstairs has to be Mordelic. So sort of from bounding rational points here, you can get bounds on the rational points of the curve downstairs. Now, of course, these are both curves of genus 1, and so neither in general has finitely many rational points, but we could use exactly the same idea to bound the group of rational points over K modulo the image. So it's the same idea, okay? But I want to kind of maybe make this a little bit explicit and sort of introduce some vocabulary, the vocabulary of descent, which I'm going to be using tomorrow and on Wednesday when I discuss the underlying proof behind, the ideas behind the proof of Colli-Wagen's theorem. So I want to kind of have a few notions behind my belt. So the way that one kind of phrases this argument in modern language is to consider the so-called Kummer exact sequence, the multiplication by n map on the elliptic curve, which as a morphism of algebraic curves is surjective. So if you want over K bar, it's a surjective map. And the kernel is the module of n torsion points of E defined over K bar. Now we can take the Galois invariance of this exact sequence. So we take the GK invariance. And what we get, okay, I'm going to start here. I don't really particularly care about this. Okay, this kernel is going to be small, the invariance of En over K, the K rational points of En. So I get the following exact sequence. E of K goes under multiplication by n to E of K. But of course, this is not exact anymore, right? That's the whole point. That's certainly a basic example where you can see that the functor of taking invariance is not exact on the right. And so there's a co-kernel, which is the first cohomology of the Galois cohomology, H1 of GK, with values in this Galois module En. And the co-kernel of this map is the n torsion. Okay, I could continue. I would get the H1 here and the H1 there. So it's the H1 of GK with values in E, or in E of K bar, but the elements which are killed by n. So this is actually a surjective map. And of course, in this exact sequence, everything is fairly clear. The important map to understand is this one, which is called delta. Okay, so what we have then is a natural injection from E of K mod n E of K into H1 of GK E n. H1 E n torsion. So we have this sort of fundamental three-term exact sequence which embeds the group we're interested in into this kind of Galois cohomology group. Now, this argument I made, of course, applies to any field. I could have done the same thing over the various completions of K. And so I have a corresponding local exact sequence for every completion of K. So I have so-called, corresponding local connecting homomorphism to the Galois cohomology En, and the co-kernel is likewise, E of GKV En. And the natural embedding of K into its completions induces natural maps like that. So, the idea would be, okay, if we could show that this group were finite, for example, then that would give us immediately that this quotient is finite, and that would give what's known as the weak Mordell-Weil theorem, that E of K mod N E of K is finite. Okay? Well, unfortunately, this group is not. It's actually rather large and infinite, but we can try to cut down its size by imposing various local conditions. So considering only the classes which, when you look locally, look like they come from points, or do come from points over the various completions. In other words, taking the classes which are in the kernel of this map. Okay? And that's what's called the Selmer group. Okay? So the N-Selmer group of E over K is the kernel of the natural map from H1 of, okay, instead of writing GK, I'll use the standard convention from now on and write H1 of K with values in En. Okay, that means the same thing. We've seen that already a number of times. The natural map to H1 of KE V, H1 of KVE and torsion, where I take the direct sum over all V. Okay. So then there are two kind of stages in showing that this group here is finite. The first is to show that the N-Selmer group of E over K is contained in a subgroup of this H1, which I'll denote by H1 sub N delta of KEN, which is just the classes which are unramified outside N delta. And that's sort of, we've seen this kind of argument a number of times. The point is that if you take a point, maybe I should say, this is an exercise that if you haven't seen it before, you should definitely do. So, is to write down delta. Okay, write down a specific formula for delta. I'll give it to you, in fact. So if you take delta and you evaluate it on a point, you get a function on the Galois group. And what is delta of P evaluated on sigma? Well, it's just P tilde applied, sigma applied to P tilde minus P tilde, where N times P tilde is equal to P. So you just choose a P tilde, which is a lift of this point P under this map, multiplication by N. And then you sort of study the failure of this point to be defined over K, which is measured by this cocycle. Okay, that's the formula for delta. And what you see from that is that, you can make a local analysis then and see that these cocycles are unramified outside the primes dividing N delta. Okay? That's the first point in the proof. And then you make a global analysis, and H1 N delta of K En is finite. That follows from the theorem of Hermite by exactly the same kind of arguments that we saw last week. We saw this kind of thing a number of times. You have these cocycles essentially correspond to finite extensions of the field of N division points with bounded ramification, and so therefore there have to be finitely many of them. That's sort of the flavor of the argument, and that leads to the conclusion that E of K mod N E of K is finite. So we've done this by embedding into this Selmer group, which is this sort of Galois theoretic object. Yeah. You have a question? Well, I don't know what to say. We saw this a number of times last week. We discussed, I've used this word unramified in the concept a number of times. And if I really go into the details now, I'll run over time. Yeah. Yes, for this, yes. I'm glossing over some details here. You see, well, I have an embedding of K into KV, right, which is a natural embedding. But then you're right that if I want to look at what is this map from GK to GKV, it's a restriction map. So I have to also choose an embedding of K bar, into KV bar. And there are many choices, but all these are defined up to conjugation. So you just choose one for each V. It's independent of the choice. For that, you'll just have to trust me. I mean, take my word for it. Okay. So, okay, so that's what's called the weak Mordell-Weil theorem. Of course, this is only half the proof because in order to show that E of k is finally generated, we have to have some kind of discreteness statement about the group of rational points. So the extra ingredients is heights. So there's the notion of heights on this group, which sort of tells us that the group has the right kind of discreteness property that we can then conclude finite generation from this. I insist on the first half, the weak Mordell-Weil theorem, because that's what's going to come up later in my talks. In a sense, it's really the sticky point in the proof of the Mordell-Weil theorem. That's where somehow the lack of effectivity, I'll discuss this more a bit later, I think. I mean, so it sort of underlies our basic approach to understanding E of k is to embed it in the Selmer group. So now maybe I should say that we have this exact sequence which embeds, so having cut down, taking this n Selmer group, we have the exact sequence which maps the group of k rational points modulo n to the n Selmer group of E over k. And the kernel is the so-called Shafrovich-Tate group, which you've certainly seen a number of times in various guises in various of the other lectures in the last 2 weeks. And the Sha of E over k, the n torsion of Sha, right? Where the Sha of E over k is the kernel of H1ke into the natural map into the direct sum of the H1kve. And this is identified with the curves of genus 1, which locally are isomorphic to E, which locally have a rational point over each completion, but are not isomorphic. The isomorphism class is over k of such curves of genus 1. And so that's the sort of basic exact sequence. So this is the object which you can try to compute. In various descent arguments, we try to compute this and thereby obtain bounds on E of k mod n E of k. On the other hand, we can certainly try to find points by exhaustive search or so on. And we hope that these two processes of bounding E of k from above and from below are eventually going to converge. And the obstruction to making a firm statement in that direction is precisely this group, understanding this mysterious Shafrovich-Tate group. What did I say? Oh, yes, sorry, kernel of this. Yeah, I didn't finish what I was writing, yeah. Okay. And the direct sum over V, yeah. No, so this is actually, I can write the direct product if you want, but it's a fact that this actually maps into the direct sum. So if you have a principal homogeneous space, it's going to acquire local points almost everywhere. So this is going to be 0. If I had the n inside, of course, it would be a different story, right? The Selmer group, so for the Selmer group, I hope I wrote, yeah, I did write it. Here I also have the analysis. I think it's okay what I wrote. Okay, so that's all I wanted to say about Mordell-Weil, about the proof of Mordell-Weil. We'll be going back to that when I talk about Colli-Wagen tomorrow. Now, so maybe let me write down some of the fundamental questions in the subject. So the first maybe is to decide when R is 0. Okay, so get a criterion that'll tell us that the rank is positive, that there are infinitely many rational points on the k rational points on the elliptic curve. Give a nice criterion. The second, which is in line with some of the computational themes in this summer school, and anyways, certainly the fundamental problem anyway in the theory of elliptic curves, is the problem of computing R. So you're handed the elliptic curve and the number field, and you actually want to compute E of k, or compute the rank, maybe compute a system of rational points. I mean, maybe compute R and maybe a system of generators, P1 up to ER, generators for the group E of k modulo its torsion subgroup, for example. So those are sort of fundamental problems which we don't know how to do, in this case coming from the fact that we can't really control this Shafrovich-Tate group and prove its finiteness, for example. So what little we know about these questions well, is formulated in the Bertrand and Dyer conjecture. So I want to now explain the Bertrand and Dyer conjecture, which already made kind of a cameo appearance, I mean actually an important appearance last week, when we discussed Mazur's theorem and gave a criterion for the finiteness of various quotients of J naught of P. Okay? But now I'm going to try to kind of be a little bit more systematic in explaining the Bertrand and Dyer conjecture. So the basic insight, so let me just now, to simplify, suppose that the ground field K is the field of rational numbers. Okay? Just to simplify my notations. And nothing I'm going to say here is really essentially tied to Q. Well, so the basic insight is that we would like to kind of say that there's a kind of local global principle. So for every prime P, say not dividing delta, we can define the number NP by counting the number of points on the elliptic curve over the finite field with P elements. And the basic feeling is that if the rank is large, then that means there are many rational points, and by reduction mod P, this rational point should contribute systematically to the size of E of Fp. So we would sort of think that the NPs would tend to be rather larger when the rank is large. So that was sort of what got to Bertrand and Dyer their initial insight. And what they did is they considered the following partial products: the product over all the primes less than some capital X of NP over P. And the heuristic observation they made was that this grows like a constant, depending on E, which in any case they weren't able to determine really precisely, times a certain power of log X. And the power that came up appeared to be the rank. So they did this calculation for various elliptic curves whose rank they knew in advance. And this was just a heuristic observation. So this was based on numerical calculations by Bertrand and Dyer on a number of elliptic curves. So this is an instance of a kind of local global principle because it tells you that the NPs, which encode local information about the elliptic curve, somehow know about this global invariant R, the rank. Okay. So there's a sort of more, there's a more useful way, more sophisticated, but more useful way of formulating this kind of basic insight in terms of L functions. So we associate to E the Hasse-Weil L function, which I also mentioned last week in connection with the Abelian varieties and Elliptic representations. This made an appearance in our discussion of Mazur's proof. The Hasse-Weil L function of the elliptic curve is defined as an Euler product over all the primes not dividing delta. So here delta I'll take to be the minimal discriminant, assume that E has a minimal form somehow. 1 minus AP p to the minus s plus p to the 1 minus 2s inverse, where AP is just the discrepancy between the number of points mod P and P plus 1. Okay, there's this, and then when one completes it for the primes dividing delta, there's a formula of this shape where AP, in this case, is 0 or plus or minus 1, okay, depending on the kind of bad reduction that the elliptic curve requires. It's not very important. But maybe to motivate this definition from a naive point of view and connect it with what I wrote here, okay, you could observe, there are two facts about this elliptic curve, about this L function. So LES converges for the real part of S bigger than 3/2. And this is an exercise, I already did this exercise last week when I discussed the L functions attached to abelian varieties or elliptic representations, when I made the statement that the elliptic representations were what I called rational. And that came along with a bound on the Frobenius eigenvalue. And in this context, it means that these coefficients AP are less than 2 square root P in absolute value. And from that, you can make this conclusion about the absolute convergence of this product on the plane to the right of S equals 3/2. So, okay, but if you look formally, so if you do something which is completely illegal because you're outside the domain of convergence, But if you expand LE1 formally, you'll find that you get the product of P over NP. Over all P, more or less, right? Just plug in S equals 1. So the idea is that, from that, you kind of postulate that the behavior of this L function at S equals 1 reflects something about the size or the asymptotics of the growth of the partial products, the corresponding partial products. Okay? And so that's what kind of motivates, maybe with the help of some hindsight, the Bertrand and Dyer conjecture, as I'm going to state it now. Okay, so let me erase this. So there are two conjectures. Well, okay, let me just write the conjecture in the following way. So conjecture BSD. So I should say that, this L series, which I defined for Q, there's a similar kind of thing where you could define the Hasse-Weil L series of the elliptic curve over K, okay, is similarly defined. You just, instead of taking the Euler product over the rational primes, it would take the Euler product over all the primes of K. Okay, so it's the same idea. And so the Bertrand and Dyer conjecture is that this L series has an analytic continuation. And the order of vanishing at S equals 1 of the L function L of E over Ks is equal to the rank of the Mordell Vega group E of K. So this R that appears in the decomposition of, so the sort of the minimal number of generators you need to generate E of K. So that's the Bertrand and Dyer conjecture. There's also a, yeah. Yeah, but formally, yeah. Maybe I put it in quotes. Okay, it's really just a kind of. Yes, right. Yeah, because you see what you're picking up in the experiments of Bertrand and Dyer, the NP came in the numerator. Here, when it's sort of getting the inverse of that. So if this kind of asymptotically grows fast, then this one should sort of, if this kind of diverges, this one should sort of diverge to 0, this product. And it should diverge to 0 sort of more quickly the larger the rank R is. So it translates into the statement about the order of vanishing. That's sort of a metaphysical thing because, of course, no. This is taken as a product over primes, and likewise, this L function is taken over as a product over the finite primes. Yeah. I think so. Yeah, I think that was part of their. This certainly predated Bertrand and Dyer, the expectation that these L series would have analytic continuations. I'm sort of stating it as part of the conjecture, although, yeah, it's kind of really too. We saw this conjecture last week for elliptic curves over Q on Friday. That's just the Shimura-Taniyama conjecture. And sort of the natural generalization. This first thing is sort of the natural generalization of Shimura-Taniyama over number fields, which is certainly believed, to be true. And I'll be saying some more in the next days about sort of, okay, so anyway, let me now say something about, also, this is the statement of BSD as it appears in the Clay website, in the $1 million, so this is a Clay summer school. I'll leave it at that, right? There's a more precise version which also expresses the leading term of this L series in terms of various invariants associated to the elliptic curve, including the order of this conjecturally finite Shafrovich Tate group. So I'll suppress that. This would already be kind of a major chance, and would earn you $1 million if you can prove that. So let's see. So what do we know about this? And in the next, until Wednesday, I'll be placing myself in the context where the field of definition is Q. So from now on, I'm really going to seriously assume that the ground field is the field of rational numbers. Okay? And so in that case, it turns out we know quite a bit about this Bridgeman-Dyer conjecture, although there's still also a lot that we don't know. But so the first theorem is the one that we saw last Friday. Theorem Wiles and a number of other people. I mean, the last result in this direction, which sort of finished this line of inquiry, was a result of Breuil, Conrad, Diamond, Taylor. And I should also put the name of Hecke here. I mean, so the L series then, the Haseve L series LES, does have an analytic continuation. So we at least can talk sort of legitimately about the behavior of this function at s equals 1. That's the first result we know. So this is a general result about. And the second theorem, which follows by combining two different pieces of work, one by Gros-Saguier and the other by Colli-Wagen, is that we know this BSD conjecture if the order of vanishing of the L function is not too large. So if the order of vanishing at s equals 1 of LES is less than or equal to 1, then BSD is true. Namely, the rank of E over Q is exactly what it's predicted to be by the BSD conjecture, either 0 or 1, as the case may be. Those are the two main results we have about the Bridgeman-Dyer conjecture. So we know it for small analytic ranks, and I guess there are two directions where one can try to go further. One is to try to tackle the case of higher analytic rank over Q, which seems extremely difficult. And the other is to try to extend this result to number fields, which is what I'll be discussing maybe in the last few days of this week. So the key notion for understanding these two results is the notion of modularity, which I already introduced and explained last week. Okay, so the key, what do I want to say? The key to both results, okay? This is really the key to both results, both this theorem of Wiles and so on, and the theorem of Gros-Saguier, is the connection with modular forms. So that was the theorem of Wiles, which I stated, Wiles and these others in this. So Wiles proved it for semi-stable elliptic curves, and then there were a number of refinements of the technique, and eventually that led to showing that all elliptic curves were connected to modular forms in the sense I'm about to state. So the statement is that if E over Q is an elliptic curve over of conductor N, then there is a normalized eigenform of weight 2 on the Hecke congruence group gamma naught of n. So we saw last week what these things mean, such that E is isogynous to the abelian variety quotient. In this case, it's an elliptic curve quotient. A sub f is isogynous to A sub f, which, remember, is the quotient of J0 of n associated to f by the Eichler-Shimura construction, which I described last week. Okay. So, so consequences of that. So well, the first was one that we already, part of the Eichler-Shimura construction we saw was that, when you look at the Hasse-Weil series of this abelian variety quotient, you get the Hecke-L series attached to the modular form, okay? So the first consequence is that the L series of E, which is, it's the same as the Hasse-Weil series of AF because these are isogynous elliptic curves, and this is equal to the Hecke-L series associated to the modular form, which is just the sum of an n to the minus s, n going from 1 to infinity, where, these are the Fourier coefficients of the modular form f. Another way of writing it, I guess if I look at 2 pi to the s, gamma of s, times LES, okay? So I modify my L function by these factors. And someone asked me about Archimedean, about how we define the L function. So the L function is always defined as a product over the finite places of the number field. But when one wants to write down in a nice way the analytic properties, and notably the functional equation, it's better to multiply by certain gamma factors. And these correspond in a precise way to sort of Euler factors at the infinite places. And so this completed product has a nice expression in terms of f. So it's essentially the Mellin transform, the integral from 0 to I infinity, f of, 0 to I infinity, f of y, y over I to the s, dy over y. I think, I might be off by a power of pi here. I'm not sure, but this is more or less what it is. So you're expressing this L function essentially as a Mellin transform of this analytic function whose growth properties are well understood, and this integral converges for all values of s, and that gives the analytic continuation. So that was the idea of Hecke, that this Hecke-L series has an analytic continuation. So this gives the analytic continuation. That's the first theorem of the L series of the elliptic curve. So that's why we know that the L series has an analytic continuation, because we know that it's A sub f for some modular form, f. But there's another consequence. So that sort of explains why we know this first theorem. But what about the second? Well, there's another structure that comes along with this modularity, which is the fact that we now know that our elliptic curve appears in the Jacobian of this modular curve, x naught of n. Okay? So the second consequence is that there is a map, there is a morphism. Well, obviously, I can embed the modular curve x naught of n in its Jacobian by taking a point p to the equivalence class of the degree 0 divisor p minus infinity, where infinity is the distinguished cusp corresponding to I infinity. And then, by construction, A sub f is a quotient of J naught of n. It's what you get by modding out by an appropriate ideal in the endomorphism ring generated by suitable Hecke operators. And then the theorem of Wiles and so on and others is that this AF is isogynous to E. Let me assume for simplicity that it's actually equal. Okay, I can always replace, for these various arithmetic questions, I can always replace an elliptic curve by one which is isogynous to it without changing the questions in an essential way. So I'm going to actually assume here, from now on, that E is actually equal to this abelian variety A sub f. And so this is just a natural projection. Okay? And I'm going to call this map, this whole composite map, I'll call it phi, capital Phi. And so this phi is called the modular parametrization attached to E. Okay. What is it? No, it's a very interesting question. I mean, there's a lot known. It depends what you want to know, I guess. Yeah, so those are very important questions connected to the ABC conjecture and various other things. So there will be all sorts of wonderful consequences, Diophantine consequences, if you could bound the degree of the modular parametrization sort of solely in terms of the conductor. Now, in Weil's proof of the Shimura-Taniyama conjecture, this theorem that I stated here, is also based on understanding something about the degree of the modular parametrization. But what Weil's needs to do is to relate this degree to an invariant that's related. So this degree can be related to a certain L function, to the value of the L function of the symmetric square of an elliptic curve. And what Weil's needs to do is relate this L value, or the degree, that's the same thing essentially, to the order of a certain Galois cohomology group. So it's a more modest goal because, you have these two invariants which a priori we don't understand on their own somehow. The degree on the one hand and the order of a certain Galois cohomology group which is related to deformations of certain Galois representations. Neither of them can understand, but what Weil does is to relate the two and show that they're essentially equal. Okay? But having a control solely in terms of the conductor would give a lot more arithmetic consequences about sort of ternary type Diophantine equations in the spirit of the various Fermat equations and generalized Fermat equations which we saw last week. That would be extremely interesting because we would get much stronger results like ABC, but we're far from being able to do that. Yeah, that's exactly what I'll be saying now, actually. I'm going to say a few words about that. About sort of, basically what you're asking is sort of how we can actually understand this phi and maybe compute it eventually in terms of, There's some other comment? Okay. So this is called the modular parametrization, and I want to kind of make a comment about how you compute it. Yes. So computing phi. Well, it's a fact that if, maybe to be safe, let me assume that n is square free. I'm not completely sure about okay. So the fact is that if we take the Néron differential on the elliptic curve, so omega e is the Néron differential. So it's sort of dx over y, but for a particularly well-chosen equation which has reduction as much as it can. Then the pullback of this Néron differential is the differential associated to the modular form, f, which is 2 pi I f of z dz, which I can also write as the sum, n equals 1 to infinity, of an q to the n dq over q. Okay, so this fact was already used by Marussia Reboledo in her lecture when she gave the explicit criterion for formal immersion of the map from J naught of n to these quotients. So if you remember, she used the fact that when you have differentials on this on various quotients of J naught of n, they pull back to sort of normalized eigenforms. So you can take the first Fourier coefficient to be 1, or at least to be a unit in the ring which she called Z, okay, which was a reduction of. Yeah, so there's a Manning constant, exactly. There's this Manning constant, which, so am I saying something which is not quite correct? I think it's known to be 1. What's the status? No? What? Sorry, I don't understand. What? So, okay, I mean, so yeah, so, okay, what you can say for sure, without working hard, is that this pullback is a certain constant times this omega f. I mean, you can show that the Hecke operators act on this pullback in the right way, so that it belongs to the same line. The question is, what is this constant? And this constant is certainly in the case of gamma naught of p, which was discussed by Marussia. In the original paper of Maser, it was known to be a power of 2. Okay, so we knew enough about this. So there were problems in characteristics 2, but I believe that now this has all been sorted out. No? You're not. So what's known? I mean, plus or 2? So it could be 2. Okay. So, okay, I mean, so there's a C here which is either plus or minus 1 or plus or minus 2. I see. Anyway, it's okay, it doesn't really matter. It's believed to be plus or minus 1, I guess. So this is the story, okay? So the pullback of omega E is this explicit modular form, the differential associated to this form of weight 2. And therefore, we can compute the image of tau. So we can get an analytic formula for phi of tau, where tau belongs to the upper half plane. And the analytic formula is this. Well, okay, what is phi of tau? I'm going to sort of write down, rather than phi of tau, I'm going to write the integral from 0 to phi of tau of this Néron differential omega E, which is the complex number in C modulo the Néron lattice, which corresponds to the elliptic curve, right, to the rational point on the elliptic curve. And this is just the integral from 0 to tau of the form omega f, if you grant me this Manning constant business. And then this is just, you just compute the integral in this convenience, since we know the ANs, so this is just the sum of AN over N, Q to the N equals 1 to infinity. And I should say that we have completely explicit expressions, of course, for these ANs, because these ANs are exactly the same coefficients that occur in the Hasse-Weil series of the elliptic curve, which is essentially the product over P of 1 minus AP P to the minus S plus P to the 1 minus 2S inverse. Okay, so these coefficients, you can compute them concretely by counting the number of points on the elliptic curve over various finite fields. You package them together in this generating series, and then you get this formula for the modular parameterization. So as a map of curves over C, if you view x naught of n as being the quotient of the upper half plane by gamma naught of n, you have a very nice formula for this map. Okay? Even if you can't write down an equation for x naught of n, which is rather hard to do in general. Yeah. This does not depend on? No, it depends on tau. I mean, tau is my, oh, sorry, q is e to the 2 pi I tau, yes. Yeah, now it's not the formal thing. I'm plugging in this value of q, and I'm getting a complex number. I mean, so this q is now really on the open unit disk in the complex plane. Okay, so I mean, what's the so this map is so phi is a map of algebraic curves defined over q. Okay, but it's very hard to write down an equation for x naught of n over the rationals. But on the other hand, there's also sort of explicit control over this map as a map of curves over C via the identification of this with H mod gamma naught of n. Now, the main use of this modular parameterization arises via the theory of complex multiplication. And that's the next thing I want to treat. I mean, so you see, now that you have this map from the modular curve to an elliptic curve, a strategy you could adopt for computing rational points on the elliptic curve is to try to find rational points on the modular curve and then map them over to E. Now, of course, that kind of strategy is doomed because these modular curves x naught of n are curves of higher genus. And we kind of know from Faltings that there are very few, we know that rational points on curves of higher genus are very scarce, so there are very few of them. And also, from Mesa's result, we sort of bounded the number of rational points on x naught of n as n gets large, and we kind of expect that there are no, we know, in fact, that there are no rational points for n large enough. So, okay, but anyway, you still try to do this. You look at x naught of n, map to E, and the question is to find rational or algebraic points on the modular curve x naught of n. And these would give rise to algebraic points on the elliptic curve by virtue of the fact that this phi is defined over the rationals. Now, we know from the start that if we are successful in making such collections of rational points, they're going to have to be defined over larger and larger fields of larger and larger degree, probably because, well, maybe not. But anyway, so that's sort of the idea. That's the strategy. Once you have an algebraic point on the elliptic curve, then you're kind of in good shape, because thanks to the group law, you can look at the sum of all the Galois conjugates of that point, and you have at least a hope of manufacturing a rational point on E once you've made an algebraic point. Okay? So that's the idea. And so then you ask yourself, what are sort of what are the algebraic points on x naught of n that we know about? And the answer is, of course, the CM points, the points which correspond to moduli of elliptic curves with extra structure, namely with somewhat larger endomorphism rings that we. So I want to now talk about CM points and Heegner points. So let me fix a K, a quadratic imaginary field. Okay, so I take a quadratic imaginary field, I mean a field that you obtain from the rationals by joining the square root of a negative integer d. So d is positive. And I give myself an embedding of this quadratic extension of Q into the complex numbers. And then the main result, the main theorem, is that if I take a point tau in the upper half plane, which also has coordinates in this quadratic imaginary field, then the image of this tau under phi is actually an algebraic point. Then phi of tau belongs to E of, in fact, it belongs to an algebraic extension of K, but it's an abelian extension of K. So it belongs to E of K ab, where K ab is the maximal abelian extension of this quadratic imaginary field K. So I should say here that I'm identifying phi with its analytic realization as a map from the upper half plane to the complex points of the elliptic curve. Viewed in this way, phi is a highly transcendental map. So you kind of expect that if you start with a tau, which is algebraic, you would get a phi of tau, which is transcendental. And that's essentially true with this key exception, that for quadratic imaginary rationalities, you get algebraic points, in fact, points defined over abelian extensions. Okay, this is quite a striking result about the algebraic nature of these values. And we'll be hearing a lot about CM points in the coming lectures, notably, I guess, on, the lectures of John Voigt tomorrow or Wednesday are going to talk about some arithmetic applications of these. Oh, okay, wait, sorry. Yes, that's known. That's a theorem. It's known. So for values of the modular function j, it's known that, which is exactly what you need for this, right? So it's known that if tau is algebraic and not quadratic irrationality, then j of tau is transcendental. Okay. What do we want to say now? Maybe. So tomorrow I'll maybe define these points a little bit more carefully. So I'm running a little bit of time, so I'm going to kind of just make a little summary of what I want to talk about tomorrow. Okay? So what we'll do tomorrow is we'll define a bit more carefully these systems of CM points, and we'll prove two main theorems about them. Okay. So tomorrow we'll see that for certain k, for certain judiciously chosen quadratic imaginary fields, we can obtain, and for certain values of tau also that are well chosen, we can obtain a point P in, well, you see, it wouldn't be reasonable to expect that we would always obtain points on x naught of n over k, because that would sort of give you many degree 2 points over k. But we can obtain points over the Hilbert class field, which I'll call P1, on x naught of n of h. And, or maybe, let me call it Q, I guess, Q1. And then I can define a point pk by taking the trace from h down to k of this point phi of the image of this point q1 under the modular parameterization. So I have a point, a CM point on x naught of n, whose coordinates are in the Hilbert class field. I take the trace down to k of the image of this under phi. I get a point, therefore, in E of k. And so there are two basic theorems about these points. This point, I'll explain its construction tomorrow, is called the Hegner point, associated to the imaginary quadratic field K. So there are two results that we know about these. The image under phi, exactly. So I take this point Q1, I look at its image under phi, I get a point on E of h, because phi is defined over Q, and this point is defined over h. Then I trace this point. No, Q is defined over h. Right? No, but now I've traced. So this point, which is an E of h, I've taken its trace down to k. So trace means I look at the sum of the Galois conjugates for the action of Galois of h over k. So I look at the sum of these points, and this is going to be a point over k. Yes. Yes. Tau is defined over k, but q is not. No. So this is important to kind of insist on. You see, this theorem, right? When I write that x naught of n over c is identified with h mod gamma naught of n, okay? This isomorphism is analytic. It does not respect fields of definition. So it's a remarkable fact that if you take a quadratic imaginary tau, it corresponds to an algebraic point here. This algebraic point is not defined over k, it's defined over an abelian extension. So I wrote here k ab. It's a certain abelian extension of k. So this tau, in this case, if we choose tau and k carefully, we can actually produce in this way a point on x naught of n, which is defined over the Hilbert class field. Let me write it down. H is the Hilbert class field of k, which is a certain abelian extension. So it's the Hilbert class field of k. Mapping it down to E, I get a point in E of h. Then I'm tracing it down to k, I get a point in E of k. And we'll see two key results about this point pk. The first is a result of Gros-Zagier, which relates this P sub k to L series. And it says essentially that the first derivative of the Hasive L series of E over k at 1 is equal to the Néron-Tate height of this point pk times an explicit non-zero fudge factor. So the appearance of the Gros-Zagier formula is this one. It says that these two quantities are related up to a non-zero factor, which means in particular that So the main consequence is that if L prime of E over K1 is non-zero, in other words, this L series has an order of vanishing 1, then then pk is of infinite order. In fact, I guess this is a logical equivalence, okay? I mean, both things are equivalent because the point is infinite order precisely if its Néron-Tate height is non-zero. So we have that. So we have a control over this basic point via, I mean, in terms of the L series, this way. That's the first theorem. I'll call that maybe theorem A. The second theorem, theorem B, is going to establish a connection between this point pk and the Mordell-Weil group of E over K. And the theorem, and this is due to Colli-Wagen, is that if pk has infinite order, so if this method for producing a rational point on the elliptic curve works, then, in fact, E of k is generated by this point. E of k modulo the group generated by pk is finite. So, I mean, you see, in the Burson-Dyer conjecture, you're trying to relate L series to E of k, or to E of q, right, to Mordell-Weil groups. And so the connection between those things is postulated by the Burson-Dyer conjecture. And what we're going to see tomorrow is that in the middle you have these sort of Heegner points. I'll explain how that connection is made tomorrow. And then what I'd like to do is to give you a good overview of I'll say very little about the theorem of Gros-Saguier, which is an essential part of the proof, but is a sort of a very computational component. So this one I won't talk about much, but I'll try to give you some good account of the methods of Colli-Wagen, which are fairly general. And of course, I remind you that these results of Colli-Wagen also play a key role I mentioned that last week, in the proof of Mazur's theorem and certainly Merel's theorem as it was presented by Marussia Reboledo on Thursday. Okay, thank you.